8th International Physics Olympiad year 1975 IPHO. I offer private tutoring for physics Olympiad preparation. I currently have openings. Message me if interested. My email is fred1996@hotmail.com, or you can use Skype name Eduard F 1996. Problem number 3. Ions in a magnetic field. A beam of positive ions, charge positive E, of the same and constant mass m, spread from point Q in different directions in the plane of paper. See figure. The ions were accelerated by a voltage U. They are deflected in a uniform magnetic field B that is perpendicular to the plane of paper. The boundaries of the magnetic field are made in a way that the initially diverging ions are focused in point A, QA equal to A. The trajectories of the ions are symmetric to the middle perpendicular on QA. Among different possible boundaries of magnetic fields, a specific type shall be considered in which a continuous magnetic field acts around the middle perpendicular and in which the point Q and A are in the field-free area. Question A. Describe the radius curvature R of the particular path in the magnetic field as a function of the voltage U and the induction B. Question B. Describe the characteristic properties of the particle paths in the setup mentioned above. Question C. Obtain the boundaries of the magnetic field, boundaries by geometrical constructions for the cases R less than A, R equal A, and R greater than A. Question D. Describe the general equation for the boundaries of the magnetic field. Solution for problem number 3. Question A. Describe the radius curvature R of the particle path in the magnetic field as a function of the voltage U and the induction B. Solution. The kinetic energy of the ion after acceleration by voltage U is this one, 1/2 mv square equal EU. From this equation, the velocity of the ions is calculated by V equal square root from 2 EU over m. On a moving ion, charge E and velocity V in a homogeneous magnetic field B acts a Lorentz force F. Under the given condition, the velocity is always perpendicular to the magnetic field. Therefore, the paths of the ions are circular with radius R. Lorentz force and the centrifugal force are of the same amount. So we have EVB equal mv square over R. And from this equation, the radius of the ion path is calculated. R equal 1 over B multiplied by square root from 2mu over E. That was a solution for question A. Question B. Describe the characteristic properties of the particle path in the setup mentioned above. Solution. And ions of mass m travel on circular paths of radius r equal this expression Vm over Eb inside the magnetic field. Leaving the magnetic field, they fly in a straight line along the last tangent. The centers of a curvature of the ion paths lie on the middle perpendicular of QA, since the magnetic field is assumed to be symmetric to the middle perpendicular on QA. The paths of the focused ions are above QA due to the direction of the magnetic field. So that was a solution for question B. Question C. Obtain the boundaries of the magnetic field. Boundaries by geometrical constructions for the cases r less than A, r equal A, and r greater than A. Solution. The construction method of the boundaries of the magnetic fields is based on the considerations in part B. Circles of radius r and different centers of curvature on the middle perpendicular QA. Sketch tangents on the circle which either point Q or point A on these straight lines. The points of tangency make up the boundaries of the magnetic field. If r greater than A, then no tall ions will reach point A. Ions starting at angle theta than the tangent at Q do not arrive in A. The figure on this page shows the boundaries for the magnetic fields for the three cases r less than A, r equal A, and r greater than A. Question D. Describe the general equation for the boundaries of the magnetic field. Solution. It is convenient to reduce a general equation for the boundaries of the magnetic field in polar coordinates r and phi, instead of using Cartesian coordinates x, y. The following relation is obtained from the figure. From this figure we have small r multiplied by cosine phi plus r sine phi equal A. The boundaries of the magnetic field are given in that case by equation small r equal A over cosine phi multiplied by 1 minus big R over A sine phi. That was a solution for question D, and here we solve all questions for problem 3.